Okay, so if you were in, um, especially if you were in Miss Dickens' class, I think she literally uses this. And this is one of those things where if you can't remember how to change atoms to ions, then you're going to have difficulty with naming and that kind of thing. So it's important, again, to make sure that everybody's on the same page. So what we're going to do today when we talk about atoms to ions and isotopes, now we are going to change the basic atom. So ions have a different number of electrons, isotopes have a different number of neutrons. Still the idea that the atomic number, which is the number of protons, is unique and can't change. So, but you can change the number of ions, which is basically the fundamental idea behind chemical reactions. And then isotopes is a branch of chemistry but deals more with nuclear changes. So an atom is neutral, no charge. So the number of protons and electrons are the same. When something is yellow, usually that means you have to write it down. But you can decide. If you want to write, you already know this, you can, you don't have to. These are your notes. And ions are going to be positive or negative. So this is why the relative charge is important. The +1 for protons and the -1 for electrons. How many are there compared to each other will tell you the charge. So atoms lose or gain. Again, sometimes we talk about a full outer shell as 8, octet. Really, some elements can have 2. And then, of course, valence are outer electrons. So when we talk about reacting or something becoming an ion, something losing, gaining, even sharing, it's always the valence electrons, and the next topic we're going to talk about is trends in the periodic table. And we'll look at why some elements are more reactive than others. And it has a lot to do with the core or the nucleus, which is positive. How much does it pull on the electrons that are around it? So that affects how easy it is to remove electrons, how greedy an atom is for new electrons to be gained. So the number of valence electrons is important, and what's going on in the nucleus is also going to be important. So we first looked at just in general, how do you find the number of protons, etc. Now we're going to look at what happens when you change it. So in a periodic table, we have rows and columns. So groups are called, or columns are groups, sometimes also called families. Not every family is a perfect column. And then rows are periods. So when there are two basic patterns, if you look at your Bohr-Rutherford diagrams, if the element is in the same row, then in a Bohr-Rutherford diagram, it has the same number of shells or orbits or energy levels. All of those things mean the same thing. You can write orbits, you can write shells, you can write energy levels, whatever you like better. So that is a shortcut or a way to check your answer. Period 1 or row 1 should have 1 shell. Period 2 or row 2 should have 2, etc. And then in the same group or same column, it has the same number of valence electrons. And that's why the families are often in columns, because the number of valence electrons can influence the reactivity or the properties, which makes them, we regroup them together. So it's not random that we call columns groups. There's a reason. And then the one thing is, we are going to skip the transition metals. So when we're going to talk about transition metals and why we don't count their columns to find the number of valence electrons, etc., we're going to look at their strange electronic structure. So like I said, number 21 is the first transition metal, scandium. And so really, I really hope that your grade 9 or 10 teacher really focused on the first 20 and not doing past that, because even the idea that the electrons travel in orbits really started to fall apart and really cannot explain the properties of transition metals. So we're going to look at those later, okay? Okay, so there are two kinds of ions. There is a positive ion or a negative ion. That's it. Those are your choices. So we are going to change the number of valence electrons that occurs during a chemical reaction. And again, only the valence electrons. They are not close to the nucleus like inner electrons are. Students always get mad at me that there was like, oh, Miss Tao, you don't leave enough space. So what I'm going to do is, for the next one, I'll show all of it, and you can write it down, and then we'll talk about it after, okay? So I won't talk over you. Okay, so this is really in words what I just said, that if you have a group, they have the same number of valence electrons, They are going to behave similarly in chemical reactions. That's why we call them groups or families. You can color these. If you happen to look at your periodic table, some of the more common groups like alkali metals, alkali earth metals, halogens, noble gases, it's actually labeled on the periodic table. They definitely have patterns of reactivity. Okay, so we'll do losing electrons first. Like I said, this is literally what we would do in grade 10. So depending on how much you remember, then maybe you're like, oh yeah, I got this, I remember this. We start on the left. Okay, so this group group 1 has 1 valence electron, which means they are, if you're trying to get to, we'll think of it as 8. If you're trying to get to 8, does it make sense energetically to lose 1 or gain 7? It doesn't make sense to gain 7. That's not going to happen. So it loses 1. It takes the least amount of energy, so it's going to lose 1. So some people will even, at the top of their periodic table, at the top of the column, they'll write up here +1. So if you lose a negative charge, you become more positive. So when you get a periodic table for the test, for example, it's not going to say +1, but if it helps you while you're doing the homework, whatever, then on your periodic table that I gave you yesterday, you can write +1. If you want to write it on this note here, you can do that too. It's up to you. So again, some of you will automatically be like, oh yeah, alkali metals, they have a charge of +1. That's fine. You can, if you need to remind yourself of how we get there, that's what the next slide does. So when you're determining what charge an ion will have, you're looking for how does the number of electrons compare to the number of protons. And remember, we're going to just use the relative charge, +1, -1. So an ion has to have a charge. If it loses electrons, it becomes more positive. Or there are more protons than electrons. Actually, I'll show you again. I don't want you to yell at me. Sounds good. Okay, so if something loses electrons, it becomes more positive. There will be more protons than electrons, which can help mathematically figure out the ionic charge. If an atom gains electrons, it becomes more negative. Now you have more electrons than protons, which again, you can mathematically determine the charge. When you do the ionic charge, even though we only draw Bohr-Rutherford diagrams for the first 20, one of the advantages of the periodic table is that every single element in the first column will have a charge of +1, or they have 1 valence electron. Even though we're not going to draw the Bohr-Rutherford diagram for francium, we are going to consider it to have 1 valence electron. So when we talk about reactivity, then the fact that francium has only 1 valence electron to lose is going to make it very reactive. So the even though we're not going to go that far with Bohr-Rutherford diagrams, you can use these patterns to predict what the charge would be. So when we get to Unit 2, the first thing we're going to do is naming. So where you have to do things like the crisscross rule and that kind of stuff. So looking at the patterns in the valence electrons and the ionic charge will be useful. So if last year you wrote +1 for this column at the top here, +2, skip the transition metal, +3, that kind of thing, you can do the same thing. We are going to name again, then we're going to balance, etc. Okay, so that's a valid pattern that you can use, even though we're not going to go that far with Bohr-Rutherford diagrams. Okay, so if you go back to group 1, so the elements in group number 1 lose 1 electron. So the groups are labeled sort of weirdly on this periodic table because sometimes you'll see it, in fact, what does this one do? I'm just going to go back to this picture for a second. So you can even see that this one goes 1, 2. It says A, skips the middle, 3, 4, 5, 6, 7, 8 to help emphasize how many valence electrons those columns have. The same thing with your periodic table, because the transition metals, the ones that are sunk here, this block here, they do have a unique electronic structure. So this one also has in brackets 1, 2, 3, 4. So just counting the columns. But when you're trying to do the patterns in electronic charge or ionic charge, that is not useful, okay, to count the columns with the transition metals, because we're going to skip those for now, okay? Okay, so they are becoming more positive by a factor of 1. The ionic charge would be +1. Some teachers I know are really particular. If you write it as +1 or 1+, I don't really care. When it's going to matter, maybe at the end of grade 12 chemistry or first year chemistry, we're going to talk about a special class of reaction, redox, where you write oxidation states like this particularly. But for us, it doesn't matter. When you do the crisscross rule, when you think about what kind of charge an ion has, writing it as 1+ or +1 really doesn't matter. In fact, we often don't even write the 1, just like math, you don't write exponent 1. Okay, so you can write it, you cannot write it, you can write +1, you can write 1+, I don't care. So sodium is a common alkali metal in the third period here. Na is its symbol. It has, as an element, has 11 protons, 11 electrons. It loses 1 to have 10. You can even do the math. I'm just going to show you. So if you want to condense this, you can. If you want to write it all out because you don't remember, you decide. Okay, so you can literally do the math. 11 positive charges plus 10 negative charges makes a charge of plus 1. That's where it comes from. Again, we don't usually write the 1, but you can choose to. It doesn't matter. I won't take marks off for that. Okay, so gaining electrons. This gaining electrons occurs past group 4 here, this carbon column, so on this side, except the noble gases, which are already 8. So if you look at group 6 here, so we'll count group 6 without the transition metals. So that TM stands for transition metals. So group 6 will have 6 valence electrons. So now if it's trying to get to 8, is it going to lose 6 or gain 2? It's takes less energy to gain 2. So group 6 is going to gain 2. So in grade 10, when you first talked about this, maybe your teacher didn't talk much about the column with 4. Perhaps they just skipped it altogether. So what we're going to do is when we are talking about losing and gaining, which is ionic and ionic compounds, which we'll review that tomorrow, this column we are not going to be concerned about until we get to covalent bonds, which is sharing, right? So, or molecules like the mono, di, tri, the prefixes. So carbon and silicon you don't have to worry about whether they lose or gain because they don't. They share, okay? And in fact, carbon has such a unique structure. There's a whole section of chemistry called organic chemistry, which does not mean chemicals grown without pesticides like farming. What it means is the chemistry of carbon. So carbon is such a unique element, it actually gets its own branch of chemistry. So you don't have to worry about this column, whether it's going to lose or gain, because it only shares. And what you're going to see is, too, we want to be able to make generalizations or find patterns really easily. So yes, we colored alkali metals, alkali earth metals, even hydrogen, transition metals, all separately. Really, what you need to be able to do is sort of chunk them as, do they lose or gain electrons? Do they become cations or anions? Maybe you remember those words. So we're going to think about the left side or to the left of the staircase as metals because they are going to be positive or lose electrons, and then the right hand side as non-metals. So these ones are going to gain electrons or become negative, okay? So we're even going to sort of push generalizations even more because that is going to be better for you. What's going to happen to it and when it reacts? How do I name it really quickly? You want to be able to see the patterns a little bit easier. So I literally have students who are like, I couldn't do this in grade 10. I couldn't do crisscross rule. I couldn't name. I couldn't balance. And then you come here and it's like your big grade 11 brains can see the patterns now and you're like, oh, I can do this. Okay? So yes, you can. Trust me. But let's go through it again, okay? So we'll go through it step by step. Elements in group 6 gain 2 electrons. Now the number of protons does not equal the number of electrons in the other way. Now you've got more electrons and protons, so it's becoming more negative. So again, -2 or 2 negative, doesn't matter. You can write it either way. Let's do selenium. Selenium is in the same group as oxygen, the same column. So it's in group 6. You're going to gain 2 valence electrons. So instead of 34, it'll have 36 electrons, which is -2. when you go to do some of the questions in the textbook, and it says draw the Bohr-Rutherford diagram, if it's got a little charge in the corner here, whether it's positive or negative, then it wants you to do the ions Bohr-Rutherford diagram. So at the end, you can see this box here, which sort of looks like the worksheet that you should have picked up. So we'll talk about how to make the Bohr-Rutherford diagram different. I know that Mr. Devine used to do that in grade 10. He would talk about the ions. If you had it second semester with the strikes and the shutdown, or maybe he had to go faster, I'm not really sure, but we'll look at how you can represent the ion as well. Okay, so really, again, what you want to be able to do, or what we're going to do next when we get to chapter 2, is the patterns. Okay, so what is a metal? What's a non-metal? What are they going to do? So metals to the left of the staircase, that's usually what we consider. They are going to lose electrons. Even transition metals, we say that they lose electrons, so they are going to be positive. It's just different how you figure out their charge, okay? And a positively charged ion is called a cation. So sometimes, I know I wrote it in capitals there, but if you write it with a T, a little T, that it looks like a positive sign, that's a way to remember. Some people will do like a cat has paws, positive. I don't like cats, so I don't think they're positive. So, you know, whatever's going to work for you. Then the other one, non-metals, or to the right of the staircase, except the noble gases, of course, they will gain electrons to become negative, which we call an anion. It's an anion. It kind of looks like onion. Maybe onions are negative. I don't know. However you're going to remember. If you don't like tricks, you can just memorize it. But it's an important difference. Cations are positive. Anions are negative. Metals will be cations, whether they're alkali metals, alkali earth metals, transition metals, doesn't matter. All the metals are going to lose electrons, and then the non-metals are going to gain. And then one last idea is the idea about isoelectronics. So protons are unique, and neutrons and electrons do not have to be. So one of the first ideas by Lewis, a man named Lewis, was that elements lose or gain electrons, and he was the first one to use the term stable octet, which is fine. Yes, many of the noble gases have 8 electrons in their outer shell, but helium doesn't, right? So it's a bit of a wonky term, but we say that noble gases, we call them stable because they have a full outer shell. So most of them 8, but one of them is 2. So when atoms lose or gain electrons, we often consider them to be stable, like a noble gas. So sometimes a question will ask you, what noble gas is an element isoelectronic with? When you see this prefix iso, that means the same. So isomer means same structure. When you do biology, isotonic means the same amount of water in solute. Okay, so that iso means same. So elements can have the same number of electrons once they have lost or gained them, okay? As a noble gas, we usually compare it to. So one of the questions asks about when whatever, they'll give you a list of ions, has the same number of electrons as a noble gas, and some of them can be the same. So if you have, so let's say you have potassium loses electrons. It loses 1 electron. So if potassium has 19, but then loses 1, it's going to have 18. Argon has 18. So it's going to be isoelectronic with argon, always a noble gas. Chlorine is going to gain 1 electron. So it goes from 17 to 18. It also is going to be isoelectronic with argon. So some of them, the metals, will lose. So you have to kind of go backwards. But some of them will gain, and the non-metals, so then you kind of go forwards. Okay? So you're literally just counting. If it has 17 and gains 1, now it has 18. Look for the element with 18. If you forget the atomic number, don't forget the little key here is on this periodic table. Okay? All right, so let's look at the worksheet. So you have a blank one there. If you're like, I can't read that, then you can look at your worksheet. You can look at your worksheet and it's the same thing, okay? The left-hand side says atom, the right-hand side says ion. I'm going to review standard atomic notation. We'll write down the ionic charge and we'll write the noble gas it's isoelectronic with. Again, I know that some teachers in grade 10 would have taken a look at this. Your textbook, one of the questions, it asks you to write square brackets in the charge. You don't really have to do that here, but you can. Okay, so so on your note page, this is not going to be on the worksheet, okay, that box there. Let's do oxygen. So when you're asked to do this kind of question, if it asks you to do the Bohr-Rutherford diagram for the atom and the ion, or just the ion by itself, it would only be the first 20, okay? So on the worksheet, it's sodium, chlorine, phosphorus, and magnesium. So we'll do oxygen. So oxygen, you've already done the Bohr-Rutherford diagram for, so you have a choice. You can go back and look at your sheet or try again and do it yourself again. So oxygen has an atomic number of 8. When we do the atom, then the charge is neutral. Electrons are 8. And then the number of neutrons, you can decide when you're doing the homework if you want to show your work so you remember what you did later. It's up to you. So you round the mass, subtract the number of protons, which is 8. And then you decide. I checked everybody's Bohr-Rutherford diagrams at the back, so now everybody's is good. You can go and look if you want later. I'll leave them there all day. All of you did the little shell things. Again, I don't care. If you want to do the circles, if you had a teacher who was psycho and made you do like the dots and perfect, compass rows, never eat shredded wheat, that's totally fine. I don't care. Because again, we're going to use them to look at the valence electrons and the number of shells. That's really the top limit we need for them. So make a nucleus. When you do the nucleus for the ion, it's the same. Okay, so you can do that at the same time if you want. And then the atom has no charge, so we're going to do 2 and 6. And then the ion loses or gains valence electrons only. So the inner ones are going to be the same. And now you have a choice, okay? So again, maybe you remember the patterns, so you can look that oxygen is in group number 6, so it's going to have a charge of -2. Maybe you remember that, okay? That's fine. You can look at this and think about if it's already 6, then it's not going to lose 6. That doesn't make sense. It's going to gain 2 to have 8. in the outer shell, so a total of 10. So it's really sort of, it's really kind of up to you. You can think of it like it would become like neon, which has 10. You know, there's lots of ways to think of this. When you do the ion for something that gains, all you have to do is write 8 in the outer shell, okay? If you want, you can make it a different color, but you don't have to. I know, I believe Mr. Devine used to, when you lost them, he would draw a dotted line. But when you lose electrons, when we talk about ionic compounds, we are going to consider that the metal loses the electrons and does not get them back. So let's say you're going to do a metal. Actually, I'll do it after. You don't have to draw a dotted line for the valence electrons. It would not be there anymore. Okay, but we'll focus on this one. So I made it a different color, but you don't have to. If you're not into colors, I'm not going to force you. Okay, so oxygen gains 2. You don't have to write the words when you do the homework, but that's what we're always thinking, okay? Maybe you already know that. So again, you can, when it says ionic charge, you have some choice. You could just write -2 or 2 minus because it's gained negativeness, right? It's gained electrons. You can think of it like +8 plus -10, which is -2. You can do the math if you like. You can write it with the symbol if you like, whatever. In the instructions, it says, oh, I didn't photocopy this one. I said, oh, and this one I just said metal or non-metal. What did I put on the note? Noble gas. So this is what it would be isoelectronic with. If you've done it correctly, has to be a noble gas. So you look for the noble gas with 10, which is neon. It is a nonmetal as well. This one, I snuck it on the worksheet because, like I said yesterday, I don't know why, for whatever reason, sometimes students forget how to do this. So you want to write the bigger number or the mass at the top, so that's 16. If you put 16, well, oxygen happens to be 16.00, but if you don't round the mass when you do the standard atomic notation, I won't take marks off, but you do have to do mass at the top and then atomic number at the bottom. So if you want to quickly sketch, if you have space there, I did calcium. It loses valence electrons, does not get them back, okay? So you don't draw, I don't want you to do this, which maybe you did in grade 10. Don't do that, okay? It literally gets rid of its valence electrons. They are gone, okay? Because what we're going to do next is talk about how the atom, when it loses electrons, it actually gets smaller. So you can literally think of it like sort of a ruthless analogy sometimes, but it's like losing its weight, okay? It's getting smaller. So I don't want you to draw those on there, okay? So when you do magnesium and sodium on the worksheet, that valence electron will be gone, okay? Okay, so we're going to do isotopes after lunch, so you have some time now. The good news is with the worksheet and then the textbook questions, they're all kind of different. So it's like a different way to ask the same question. So if you're looking for a variety of questions, they're not all the same. So that's kind of nice. The solutions for the worksheet and the homework are on D2L, so you can check your work. When we come back after lunch, we're going to do isotopes. So you should have picked that up at the back. If you didn't and still on the cart, that's what we're going to do next. Okay? So if you are a stapler, you can do this note, then the worksheet, and then isotopes if you like to staple things together, but you don't have to.